Good morning, everyone. Today's topic is Magnetostatics. It is BSc final year students, 5th semester topic. So, before going straight away into the topic, let us see what are some of the basics of magnetostatics. Magnet is very interesting field to study. So, why few materials are very attractive in nature and why few materials are not attracting other materials. All these things already we have studied in lower classes. Let us see what is there in the syllabus here. That before going straight away into the syllabus, let us see a few definitions. What is a magnetic field? How does it exist? And what form will it appear and all. And let us see the contents of the magnetic field. So, in this topic, we are going to discuss the Biot-Savart's law, Ampere's law, properties of the magnetic field due to a circular loop of conductor along the axis, then what are solenoidal field, then energy density, force on a current carrying conductor, force between two parallel conductors, torque on a loop of conductor in a magnetic field. Since it is a very vast topic, let us see some of the topics in a quick manner, and wherever the stress is needed, that means wherever the derivations are there, we will spend more time on that. So, let us look how a magnetic field looks. If we take a bar magnet and spread a sheet over that and sprinkle some of the iron fillings on that, this is the pattern we are going to watch. So, the pattern looks like this. So, let us see, this is the north pole of the magnetic field magnet and this is the south pole. And when iron fillings are spread on this and a paper is slightly tapped, we watch they are not uniformly distributed, but they are aligning in the form of some curves. So, it indicates that the field appears in the form of curves. So, the magnetic field consists of all these curves. These curves we call them as magnetic lines of force. How do we define a magnetic line of force? Let us see this video. If you see in this video, see here. From the north pole, the magnetic lines of force are starting and they are reaching the south pole. So, from the north pole they are leaving and they are ending into the south pole. So, here what can we observe? If you imagine a unit north pole is placed in the magnetic field, then it is the path followed by the unit north pole in the magnetic field. So, the path followed will be in the form of a curve. This is how we observe, and inside the magnet also they travel from south pole to the north pole. So, all these magnetic lines of force constitute the magnetic field. And let us look at some of the basic definitions of it. One is the magnetic flux, the other one is flux density. What is magnetic flux? The total number of lines of induction or magnetic lines of force passing through some surface is called magnetic flux. And the difference between flux and flux density is the flux per unit cross-sectional area, we call it as a magnetic flux density. That is equal to magnetic induction numerically. See here at the north pole, when we consider some area A, there we see a number of lines of force passing through this are this. And if you consider another area B, the number of lines of force are less in this case. So, here we can say the flux density is more here, and here we can say the flux density is less. So, we can say the strength of magnetic field is more here and the strength of magnetic field is less. So, B is equal to phi by A, and when you consider the units, it is Weber per meter square. Then, what is Biot-Savart's law? If we imagine a current carrying conductor of infinite length, we all know a magnetic field is created by moving charges. So, on a current carrying conductor, the charges will be dynamically moving. So, around this conductor, the field is created. So, what could be the strength of the magnetic field and on what factors does this magnetic field depend? It can be understood when we go through the Biot-Savart's law. Let us see, this is the magnet line of a conductor of infinite length is passing like this. So, in this we consider a small length element dl. So we consider another point at P at a distance r from this length element. So the magnetic field at this point P depends on three factors basically. One is the length of this element we consider. The second one is it depends on the distance between this length element and this point P, and the third one is the angle made by this radius vector with this length element theta. So how do they depend? The magnetic field at the point P due to this length element dl, if you consider that is equal to dB. Since dB is directly proportional to the strength of the current passing in this conductor, that is I, then it is also directly proportional to the length element dl, and it is also directly proportional to the sine of theta between them. So when you take the total magnetic field at this point P due to the entire wire, then we can get an integration factor of it. B is equal to integral of mu naught by 4 pi I dl by r square, or we can take vectorially I dl by r square into r cap by r. The next thing is, what is Ampere's law? So Ampere's law, suppose if you consider a straight current carrying conductor, as we observed earlier, it will have the magnetic lines of force around. So in this magnetic lines of force, that means the magnetic field is created if we consider any one particular magnetic line of force in the form of a circle. Then the line integral of magnetic induction around this closed curve is proportional to the product of proportional to the current passing in this, and is equal to the product of mu naught, that is the magnetic permeability and current passing through this. So integral of B dot dl is equal to mu naught I. This is the Ampere's law. Then what are the properties of the magnetic field? The magnetic field is, as we know, it is formed by charges, either steady current, that means the charges are moving with a uniform velocity, or a moving charge. Suppose if an electron is revolving around the nucleus, or it is spinning around its own axis, then it creates a magnetic field at its own. So there are two more properties we can observe. One is the magnetic flux over a closed surface is 0. That means divergence of the magnetic field is 0. What does it state? We also can understand this in a different way. The magnetic lines of force are closed loops. They are not open-ended. So whenever they are leaving at one pole, that is the north pole, they are reaching the south pole, and inside the magnet also they are traveling from south to north. That means they are not leaving the surface as a whole. That's why we can say the magnetic flux over a closed surface is 0. Then the other property is the magnetic field is not conservative. What is a conservative force? What is a conservative force? The force which the work done by a force, if it is not dependent on path, then we can say that it is non-conservative. Whereas an electric field is a conservative force, but the magnetic field becomes a non-conservative. So mathematically we can write the curl of B is equal to mu naught J, where J is the current density. Then let us look at some of the applications of the Ampere's law. So one application is magnetic field on the axis of current loop. So here we see a current loop. Here AB is the diameter of the loop, and the area, A is the radius of this circular loop, we can say, and this is the axis. This is the axis passing through the center of the loop. Let us also assume a current I is passing in this loop in anti-clockwise direction. We consider a point P at a distance x from the center of the loop. So our aim is to find the magnetic field at the point P due to the current passing in this loop. So how do we calculate the magnetic field? Let us assume dB is the magnetic field at the point P due to a small length element considered on this loop, either here or here. So if we consider a small length element here at the point A, then at the point P, the magnetic field due to A is dB, and it acts along this direction PD. So if the length element is coming at the point B, then at the point P, the magnetic field will be dB, it is along the direction PC. And what is the distance between A and P? This is according to the Pythagoras theorem, this is R is equal to under root of A square plus X square. And this magnetic field can be resolved into two components, that is dB sin phi and dB cos phi, where phi is the angle it is making with the vertical axis. Then this magnetic field is also resolved into two components, dB cos phi and dB dash sin phi. So the cos phi, dB cos phi component and dB dash cos phi component both are equal in magnitude but in opposite in direction. So they cancel with each other because B happens to be a vector quantity. And coming to the horizontal components, dB sin phi and dB dash sin phi both are acting along the same direction. So the vectorially both are added, both are summing up here. So we can understand that the whole loop is divided into a number of components, and the magnetic fields of each component is considered here. The vertical components due to each opposite length elements will be cancelled, whereas the horizontal components are added up. Since it is a continuous flow of current, if we want to find out the total magnetic field at the point P, then this dB can be integrated. Then we can get a result like this. So it is integrated between the limit 0 and 2 pi a. Why 2 pi a? Because the circle has a circumference 2 pi a. So this is dB sin theta, because earlier slide we have seen this is dB sin theta. So in place of dB, if we substitute the value what we have taken from Biot-Savart's law, that is mu naught by 4 pi ideal by r square, and sin theta, the value of sin theta, again we can see in the previous slide, the value of sin theta here is equal to a by under root of a square plus x square. And so here if this is substituted, it comes like this. So a by under root of a square plus x square, which is the value of r, and here the value of r square is taken like this. So upon doing this integration, we can say mu naught by 4 pi is constant with respect to the integral. I is constant because it is the current passing in the loop, it is constant with respect to the integral. A, the radius of the circular loop, is also constant, and r, the distance of the point, is also constant. These all things come out of integration, whereas only the length element is integrated here, and that integration comes out as 2 pi a. So if that is substituted, we get B is equal to mu naught by 2 and I a square by under root of x square plus a square to the power of 3 by 2. This is the magnetic field at the point P, which is taken at a distance r from the axis. Suppose if we go to the center of the loop, I am taking the previous slide once again. If we want to find the magnetic field exactly at the point O, so in the previous expression we have to make x is equal to 0. Again I go to the next slide. Here x becomes 0, then this denominator will become a to the power of 3, and numerator there is an a square. So these two get cancelled, and our final result will be mu naught I by 2a. This is this answer. At the center of the loop, B is equal to mu naught I by 2a. So this is how we have to calculate the magnetic field at the center of a current carrying loop. Let us look at another example. This is a solenoid field. What is a solenoid? A circular coil of conductor, we call it as a solenoid. So if you see the current passing through the solenoid in this direction. So here we can see all these points. These points we can consider the current is coming out of the plane of paper, and through all these points the current is going inside the plane of paper. So the magnetic lines of force appear like this. They are the curves, and if we observe carefully, the density, magnetic flux density is more inside and very, very minimum outside. So we can say due to a solenoid, the magnetic field exists only along the axis, that means along only at the center of the solenoid, and this is behaving like a bar magnet. And a bar magnet, we know it will have two poles, one is the south pole, the other one is north pole. Which end of the solenoid behaves like a south pole and which end of the solenoid behaves like a north pole is the question here. So if we look at one end, if the current appears passing in clockwise direction, you can see S here, S, if we mark arrow marks at the edges, the current appears to be passing in clockwise direction. So this phase behaves like a south pole, and through this phase the current is appearing as if it is passing in anti-clockwise direction. So this phase behaves like a north pole. So this is how electromagnets are made actually. The current is allowed to pass around some rod in the form of a circular coil. We take a wire and wound it around some rod, and current is allowed to pass through the wire. Magnetic field is created at the center and the rod behaves like a magnet here. So our aim is, let us use the Ampere's law here again. We will try to find out what could be the strength of the magnetic field due to this solenoid. Look at this picture carefully. So this is the solenoid and magnetic lines of force are passing through the center. So our aim is to calculate the amount of the magnetic field at the center of the solenoid. I remind you once again, this solenoid is behaving like a bar magnet and the strength of magnetic field inside the solenoid is almost same. That means it is creating a uniform magnetic field at the center of the solenoid. So to find the magnetic strength inside, we consider a rectangular surface ABCD as shown in the figure here. So applying Ampere's law along each length element, see here the line integral of B dot dl along the total rectangular loop is equal to mu naught Ni. Actually this N is coming extra, means what? Each loop is creating for each loop the Ampere's law becomes integral of B dot dl is equal to mu naught I. So if two loops are there, the magnetic field is double. If three loops are there, magnetic field is triple. So if there are n number of turns in the solenoid, then we can consider it as the line integral of B dot dl is equal to mu naught Ni. So this can be taken as 4 parts here. So line integral means line integral of ABCD. So it can be taken from A to B once and B to C, C to D and D to A. This is split into 4 parts. This is equal to mu naught Ni. So this is the line integral of A to B, B dot dl. So line integral of A to B, B dot dl. The angle B dot dl, we know this is equal to B dl cos theta, where theta is the angle between B and dl. B, the direction of B is from left to right shown here, and the direction of length element is from A to B dl. So the angle between B and dl is 0. So B dl cos 0 is 1 as we know. So this is equal to B into, let us consider the length is L here. So this is equal to B into L. Next, the line integral of B dot dl from B to C. Here comes the problem, the angle between B and length element. So the direction of length element is from B to C, the direction of magnetic field is from left to right. So the angle between this is 90 degrees. So this will become B dl cos 90. We know that cos 90 is equal to 0. Hence the integral of B dot dl becomes 0 along this. So integral of B dot dl is equal to 0 taken from B to C here. Again the line integral of B dot dl from C to D, here from C to D. We can see there is no magnetic field outside the solenoid. So B is 0. Since B is 0, here the entire integration factor is becoming 0. Next, coming from D to A, here again the angle between this length element and this magnetic field both is perpendicular to each other. The angle between them is 90 degrees, and BDL cos theta, that is BDL cos 90 is 0. So this is also becoming 0. So BL plus 0 plus 0 plus 0 is equal to mu naught Ni. So B is equal to mu naught Ni by L. So this is the magnetic field due to the solenoid, and N is the total number of turns in the solenoid, and L is the length of this particular element AB. So if we divide these two, we get small n, which is equal to the number of turns per unit length. So the magnetic field due to a solenoid can be taken as mu naught Ni, where mu naught is the magnetic permeability, N is the number of turns per unit length, and I is the amount of current passing through that. Now, let us see what is meant by the self-inductance of the solenoid. So, the self-inductance is a factor. Suppose the current is passing inside, then it is creating a magnetic field inside. So, if the strength of current is changing, then the strength of magnetic field also changes. So, the change, any change related to a particular coil creates another magnetic field inside. This is looking quite strange here. To create a magnetic field, current has to pass, and if the current is stable, the current is constant, the magnetic field created also will be a constant. But the current, if it is not constant, the magnetic field created is also not constant. But Faraday's law of electromagnetism says that if the magnetic field linked with any loop is changing, then it creates some induced EMF, that means some induced current is passing. So these two will be interacting with each other. How? Suppose if we take a coil of conductor and we start some current to pass through. The current suddenly it starts from 0 and rises to some a fixed value. So during this increase of current, it is creating some change in the magnetic field linked with the circuit. So that change in magnetic field is creating a current which is trying to reduce the original cause which is producing it. So this kind of induction is called self-induction of the coil. This appears similarly, this appears in the same way while the current is dropping also. If we switch off the current passing through the coil, then the current drops from a maximum value to 0. So this change in the current also creates the change in magnetic field linked with the coil. This change in magnetic field linked with the coil creates again some induction into the coil, which again acts in a direction opposite to the original cause that is producing. So this is called self-inductance of a coil. So this is an inherent property. This is only related with the coils of conductor, not with the straight conductors. So whenever we are discussing the solenoid fields, we also have to discuss the self-inductance factor, otherwise it is incomplete. Let us see how the self-inductance is calculated here. The magnetic flux linked through a coil is directly proportional to the current passing in it. So if we consider phi b is the magnetic flux, it is directly proportional to the current. That means more is the current passing through, more will be the magnetic flux linked with it. So this proportionality constant is called L, that is called self-inductance. So this self-inductance is that we have to calculate now. What could be the value of the self-inductance? We all know that magnetic induction is also known as flux density. B is equal to phi b by A. So we substitute phi b is equal to B into A. B is the magnetic field and A is the area. So we know just before we have calculated the magnetic field due to a solenoid is equal to mu naught Ni. So if that is substituted, then magnetic flux becomes mu naught Nia. So the flux through all the turns of the solenoid, again it is taken as this flux through this and this will become mu naught n square I A L. Again Li, because we have calculated phi b is equal to Li, we can take Li is equal to, we substitute phi b is equal to Li here, Li is equal to mu naught n square I A L, and cancelling I on either side, we get the expression for self-inductance of a magnetic field. That is, self-inductance of a solenoid is equal to mu naught n square A L, where n is the number of turns per unit length of the solenoid, A is the area of the cross section of solenoid, and L is the length of the solenoid. Let us see how to calculate the energy density of the magnetic field. Any field will have certain energy in it, any field, because in order to do some work in the field, the work is either done on the field or work is done by the field. This is done at the expense of the energy which is present already inside. How to calculate the energy inside the magnetic field? The work done in establishing a current I in a solenoid is stored as energy in the magnetic field. So, the energy of the magnetic field is calculated as this. Why some work is done? Why some work is done in order to establish a current I in the magnetic field, coil of conductor? This is the problem. As I told you before, when we are passing some current in a coil of conductor, due to self-inductance, it is creating some induced currents are created against this direction. So, in order to overcome this induced current, it is doing some work, the field is doing some work. So, how much work is done by that and how to calculate? Let us look at this slide. So the work done in order to establish a current I in a solenoid is given by U is equal to half L I square, and in place of L we have to substitute mu naught n square AL, which we have calculated before. So, U is equal to half into mu naught n square AL into I square. So, on rearranging the terms like this, we get half mu naught n I, the whole thing is taken as a square because we have squares in n and I here, but since there is no square for mu naught, we are dividing and multiplying this with a mu naught again. So, mu naught n I whole square by mu naught into AL. And we also have calculated mu naught Ni is the magnetic field at the center of the solenoid. So, that is substituted, mu naught Ni is equal to B. So, U is equal to half B square by mu naught into AL. So, again, what is AL? A is the area of cross section of the solenoid and L is the length of the solenoid. By taking the product of these two, it gives us the volume of the solenoid. So, if we divide this energy with the volume, then we get energy by volume, which is equal to the energy density. So, the energy density of the magnetic field is the total energy by volume of the solenoid, that is equal to half B square by mu naught. This is how the energy density of the magnetic field should be calculated. Then, let us look at how the force on a current carrying conductor in a uniform magnetic field to be calculated. We know that if a charged particle which is carrying a charge q is moving with a velocity v in a uniform field of strength B, then the force acting on the magnetic field is equal to q into v cross B. What is v? That is the velocity of the particle. So, the velocity of the particle is nothing but the length by time. So, if that is substituted, F is equal to Q into L by T into B. And if this T is brought this side, because it is a scalar quantity, can be taken outside the vector, then F is equal to Q T into L cross B, Q by T into L cross B. We know Q by T, the rate of charge flow, which is equal to the strength of current passing in this side. So, if a current carrying conductor in which a strength of current I is passing and length of current is L, then it is placed in a magnetic field, it will surely experience a force whose magnitude is equal to F is equal to I into L cross B, and we know I is a vector and B is a vector, F is also a vector. The direction of the vector F can be given by Fleming's left hand rule like this here. If the first three fingers of the left hand are stretched outside and the index finger shows the magnetic field direction of magnetic field, and central finger shows the direction of current passing in that, then the stretched out thumb shows the thrust, that is the force acting on this conductor. Here we can see two such examples. Let us say a current carrying conductor is placed between the poles of a magnet like this. So we know the current magnetic field is always passing from north pole to south pole like this. So this is the current passing through this. So from Fleming's left hand rule we can imagine from N to S. N to S, this is the direction of index finger and this is the direction of central finger. Then the force will be acting in upward direction. The wire, the conductor all automatically moves pushed up. That means before the passage of current, when the current is not passing in this, the conductor looks along the dotted line. When the current is passing through that, immediately it is pushed up because the force is pushing it in upward direction. And here, if the direction of current is reversed, then the direction of force is also reversed. So in this case, the conductor is pushed in downward direction. We can take a few examples and see how the force is acting on that. But finally, this is the expression for force acting on a current carrying conductor. So let us calculate if two parallel conductors are placed, what could be the force acting on each other. So let us take two such wires in which the equal current is passing. AB is one conductor and BC is one conductor. They are parallel to each other and the distance between them is A. And the current passing in the first conductor is I1, the current passing in the second conductor is I2. So let us say how the forces are acting on this. Let us say B1. B1 is the strength of the magnetic field at this point due to the current passing in the first wire. So according to the Ampere's law, we know that this is equal to mu naught I by 2 pi a or mu naught by 4 pi into 2 I by a. This is the direction. So in this field, the second conductor is placed. Earlier we have seen it is equal to I into L cross B, but that was I L B sin theta. See the direction here, I is in this direction, that is both are 90 degrees, so sin 90 will be equal to 1. So we can take I L B, here the force acting on this conductor. So the amount of current passing in this is I2. It is placed in the magnetic field created by the first one, that is B1. So that is B1 and length of conductor is L. So I2 B1 L, if this is substituted, this is the result, mu naught by 4 pi into L into 2 I1 I2 by A. And the force acting on this per unit length, if you take FCD by L, mu naught by 4 pi 2 I1 I2 by A. This is the force acting on this conductor. Again, due to according to the Fleming's left hand rule, it is acting towards left. And this current is creating a magnetic field at this place. That magnetic field we call it as B2. So B2 is equal to, again according to the similar calculation, we can write B2 is equal to mu naught by 4 pi 2 I2 by A. Again, in this B2, a wire is carrying a current I1. So the force acting on the first conductor is I1 B2L. In the same treatment, similar treatment, we get FAB by L, that is the force per unit length is this. If we observe this, again according to the Fleming's left hand rule, the direction of the force is this. And if we see these two equations, the right hand side of these two equations is same, mu naught by 4 pi 2 I1 I2 by A, and here mu naught by 4 pi 2 I1 I2 by A. So these two forces are equal, but they are attracting each other. So if we place two parallel conductors, then they will be attracted each other. Let us look at another application. This is the torque acting on the magnetic field. this is, suppose we consider a rectangular loop of conductor placed in a uniform magnetic field. So let us assume the direction of magnetic field is B like this, and the rectangular magnetic loop, we take it as PQRS as shown in the figure. And again, according to the previous Fleming's left hand rule, it will experience some force. The forces will be acting like this. The force F1 will be in this direction, the force F2 will be in this direction, the force F3 will be in this direction, the force F4 will be in this direction. So look at these forces F4 and F2. These two are exactly opposite in direction. But what about the magnitude? What is F2? F2 is equal to I into L cross B. L is the length of this arm, which is QR, QR cross B. And what about F4? F4 is equal to this one, I, PS. This is the length element, cross B. And see these lengths, QR and PS, both are the same. So QR, this is QR, F2, and in F4, PS, both are equal. So we can say the magnitudes and F2 and F4 are equal. Two forces are unequal in magnitude and opposite in direction. So the resultant force will be 0. So these two forces cancel with each other. F2 and F4 has got no contribution on this resultant force. And let us look at these forces F1 and F3. As far as F1 is concerned, it is I into PQ. This is PQ cross B, that is acting in this direction. And F3 is in this way, this is I into RS cross B. So the direction will be opposite. These two will be, we can say they constitute a couple. We know two forces acting in opposite direction but not along the same straight line. They are separated, they are parallel to each other, and they are separated by some distance. Let us say the distance is PS here. They constitute a couple and make this arm rotating about this axis. So how to calculate this couple, the torque acting on this? We know the formula for torque is the distance between the parallel distance between the two force components. That is, let us say the parallel distance is PS, the perpendicular distance between two force components, that is PS, and one of these force elements, either F3 or F1, because both are equal in magnitude, we can take. So PS cross F3, and in the previous slide we have calculated F3 is equal to I into RS cross B. The same thing, F3 or F1, both are equal. So whether we can take RS no matter, or we can take PQ no matter. So either of these two forces and the perpendicular distance between them. So the perpendicular distance comes out to be PS here. So PS cross I into PQ cross B. So this PS is this. PS is this. So PS into PQ. What is PS into PQ? This is the product of length and breadth, that is giving us A, the area of rectangle, and B is the magnetic field, and sine theta. So this is AB sine theta. So this is the torque acting on the field. Now if you there are a number of applications for the Ampere's law. Like this, we can calculate the magnetic field given to any component in nature. That means it can be linear in nature, or it can be a two-dimensional like a rectangular structure, or it can be a three-dimensional like a solenoid. But everywhere we can apply the Ampere's law, just like we apply the Gauss law in electrostatics. The same way we can apply Ampere's law in magnetostatics to find the magnetic field intensity B at any given point. So we should remember certain facts here. The magnets are always dipolar in nature. So we can't get a single pole, because we know magnetic field is created by moving charges. Any simple charge, let us consider an electron. Suppose if an electron is moving along a circular loop, a circular direction. If we see, let us assume the electron is moving along this in the circular direction. If I see from this face, it is moving in a clockwise direction. So this is creating me or not, that is a clockwise means south pole it is created. If I see from this angle, it is rotating in anti-clockwise direction. So this face is created, anti-clockwise means a north pole is created. So for the same loop, the two faces are behaving, one is behaving like a south pole, other one is behaving like a north pole. So we can't separate both of them, both exist together, they are the dipoles in nature. So that is the only difference between the electrostatics and magnetostatics. Remaining things are a few differences. We always can compare electrostatics with magnetostatics to understand in a better way. That means the lines of force are open-ended there, lines of force are closed loops here, so that the divergence is that is del dot B becomes 0 here, whereas in electrostatics it is not 0. So in this class we could cover only certain applications of Ampere's law. We have seen certain important properties of the magnetic field, and Biot-Savart's law we have seen, Ampere's law we have seen, and applications of Ampere's law, that is the magnetic field due to a straight conductor and magnetic field due to a circular loop on the axis, that is at the center of the axis and at some distance from the axis. And we also have seen what is meant by solenoid field and how to calculate the magnetic field due to a solenoid, and we have seen what is the self-inductance of a solenoid and energy stored in a magnetic field, that is we also have calculated the energy density, then the force acting on a current carrying conductor placed in a uniform magnetic field. Similarly, the force between two parallel conductors and the torque acting on a loop of conductor placed in a uniform magnetic field. All these questions are important as far as the examinations are concerned. So I hope we have covered a few important questions here, because the subject is very vast. We cannot take up all the topics that are present in the syllabus. Maybe in the next class we can see what all are required here. So thank you for the opportunity, for the commission rate, for giving me this opportunity. Thank you one and all.